Okay. This lecture is based on chapter one of Kramer and Stewart. Okay. This is the more or less the Bible for geotechnical earthquake engineering. Okay. And the previous version was 1994, I think, or 1996. And they just recently released the 2022 version. Okay. As a background for seismic hazards, okay, it will start, of course, with an earthquake, okay, or your ground motion, and this will be followed by the response of the soil and the structure, okay, or collectively described as the system response. Which, of course, if you have buildings which are damaged, it can cause casualties or injuries. If you have bridges or transport networks, it can result in disruption of traffic and economic activity. Or if you have utilities like pipelines, electrical lines which were ruptured or disrupted by the ground movement or fault displacement, it can also result in disruption of the quality of life and other economic activities. When we are talking about hazard or seismic hazard, we are talking about a process or phenomenon, okay, which can cause harm. Okay? It can take form of a shaking or failure or landslides or dam failures, even flooding. Okay? Flooding is a rather exotic hazard because apparently when you have earthquakes and you have liquefaction, or basically when your soil loses its ability to hold structures or carry loads, it can undergo settlement, okay, which will lower the ground level. Okay, and long term it can cause flooding, and the short term it will also cause flooding because the groundwater is ejected into the surface. Hmm. Now the effect of the seismic hazards to the structures will depend on, of course, on their design. Okay. Okay. And this is a good example, the Mexico City 1985 earthquake or the Michoacan earthquake. This is significant in terms of structural engineering because Mexico back then was their earthquake building codes, okay. The philosophy of their building code was to stiffen the structures. Okay? And and when you stiffen the structures, okay, the period of vibration of structures tend to be short, so they tend to vibrate quite rapidly. Okay, and synchronize with at least for the case of Mexico, most of their medium rise structures between 3 to 6 stories. Okay, in here in the Mexico City earthquake apparently synchronized or underwent resonance with the earthquake, okay, in the 1985. So you can see here you can see mostly damaged structures in here. And in the background, or however, in the background, you have a relatively high-rise structure, which was relatively, at least it was damaged, but it did not collapse. Okay. Similarly, in the same event, structures between 1 to 3 stories were not as badly affected as those medium-rise buildings. Okay. Right? Therefore, in earthquake engineering, the vulnerability, okay, can be quite specific. Okay. Okay. So there are peculiarities or some special considerations which has to be made when designing structures for earthquakes. Okay, anyway, vulnerability. It answers the question on what would happen to the structure if it is subject to earthquake hazards or most especially the ground shaking or ground acceleration. Okay, we now also have this term seismic risk. Uh, you just have to remember that risk is all about the money involved or the lives involved, okay, pertaining to a hazard. Okay. So risk usually is expressed in terms of money or sometimes time, okay, time lost due to disruption or sometimes in terms of casualties. Okay. Okay. And normally, risk is usually obtained by multiplying your hazards, multiply it by the vulnerability, okay, and sometimes by exposure, okay. But for the case of earthquakes or seismic hazards are, or rather the exposure caused by seismic hazards tends to be quite well defined. Okay. It usually involves a rather large area. So most of the focus in earthquake hazards or seismic hazards is the hazard itself and the vulnerability of the structures or sometimes the vulnerability of the people or the human occupants. Okay. So we have an example here. Let's In this example, the hazard is a magnitude 7.2 earthquake with a probability of 1 every 100 years or an annual probability of 0.01. Vulnerability, let's say we are describing the vulnerability of a particular building or a one building which is worth maybe 1 billion pesos. Okay. So we can have a complete collapse of that building in the event of a magnitude 7.2 earthquake. And then exposure. So again, most of the time the exposure is rather predictable. Okay. So in this case, we will be setting the exposure to 1 or 100% because the building is 100% exposed to the hazard. And then the risk is simply just your vulnerability. Okay, so the vulnerability is expressed in terms of monetary cost multiplied by the hazard or the probability of the hazard, and then multiplied by your exposure. And the result is something like 10 million worth of risk per year. Okay. Now, risk usually has to be evaluated in terms of the context. Okay. We don't evaluate risk in isolation. So say for example, if the building can generate 100 million worth of revenue every year, okay, if I'm gonna evaluate that risk in terms of economics, Okay, it's a big opportunity compared to the risk of 10 million pesos, and in terms of economics, the risk might be acceptable. However, if you're going to be evaluating the risk in terms of casualties, okay, it's going to be a totally different process, or at least we have to do a separate evaluation on whether the possible number of casualties are acceptable to the society. Okay. And we usually have curves or thresholds of what is an acceptable number of casualties. We call it the as low as reasonably possible or ALARP casualties. Okay. So it's another topic for discussion we'll be covering today. Right? Now, the earthquakes, okay, are essentially seismic energy or simply just disturbances in the ground. Okay? And you have here a sketch of or a diagram of an earthquake. This is your hypocenter or the source and the subsurface. And this is the wave which is propagating initially through rock. Okay? Now, the behavior of seismic waves can change as they travel through different medium or different media. Okay. For example, usually when seismic waves hit less stiff or softer material like sediments or soils, usually the behavior is for the amplitude of the waves or the overall intensity of the shaking to amplify or increase. Okay. There are also certain cases where soil can act as filters, so they can also, in a way, absorb or attenuate motion at certain frequencies. Okay? And they can, and conversely, they can also amplify certain frequencies as well. Right? Now let's talk about the first hazard, the fault rupture. Okay? This is only usually a concern for shallow earthquakes. Okay, approximately less than 100 kilometers and depth. Okay? So when you have shallow earthquakes, the rupture in the fault can extend to the ground surface, and it can cause offsets or displacements. Okay? Which is a huge concern if you have a structure which is not easily repairable, or for example, bridges. Bridges are usually not easily or not conveniently repairable. They can be repaired, but at a great cost. Okay, you're talking here about at least a few hundred millions of pesos for a repair, and up to 1 billion or around a billion for replacement. Buildings are also quite susceptible to fault rupture because you have what we call permanent human occupants. Okay? Office buildings, for example, are occupied between maybe at least 18 hours or 16 hours a day. Okay, schools maybe around that time, but of course um you also have to consider that these are occupied by the younger children and the youth. Okay, so on a certain extent, highways and railroads are also can also be affected by fault rupture, but it's not as serious as in the case of buildings or bridges. Okay, highways or railroads are much cheaper to repair. Okay, And the potential for casualties are usually smaller compared for buildings or bridges. Another type of structures or infrastructures susceptible to fault rupture are your pipelines. Okay. So it could be a gas, water, sewage pipelines. Okay. And this can result in environmental damage of or fires. Okay. We have here an example, the Shikang Dam. Okay. I hope my pronunciation is correct. Near Fengyuan City in Taiwan. Okay. And this was during the 1999 Chi earthquake. Okay. And apparently there was a fault directly crossing the Shikang Dam. Okay. And it's named Shelongpu Fault. Okay. And as you can see here, this is the original original elevation of the dam, and this is the uplifted part. Okay, this one. So apparently there was a fault somewhere in here, which lifted up right the right abutment of the dam by a height of 9 meters. Okay, that's quite big because most engineering structures are designed for like just 25 millimeters of displacement. Dams usually can tolerate much bigger displacements, okay, maybe even a meter, but 9 meters is probably too much even for the most modern dams. Okay, and the result is that we had of course, you can see here the substantial deformation of the dam. Okay, substantial structural damage. Okay, and of course, you can see here, I think there was some spillage or leakage in the dam. This one is a railroad in Turkey, okay, during the 1999 Kokhali earthquake. I'm not sure of the pronunciation, but it's a right lateral strike slip fault. So when we talk about strike slip, we are talking about large horizontal displacements. Okay, so apparently, okay, okay. So you have here your sense of motion here, something like this. Okay. Okay. Right lateral. So the block in front of you is going to the right. Okay. And there was a resulting S shaped buccal bending. Okay. And what's anticlimactic about this one is that the tracks were readily repaired after the earthquake by simply bending back into their original alignment. Okay, now let's talk about structural damage. Hmm. Okay, so when I say structural damage, this mostly refers to the damage to buildings and other structures simply due to the strength of the ground shaking. Okay. Okay, so there are many factors which lead to structural damage. It could be due to, of course, the sheer magnitude of the shaking. Like it's really a big earthquake, or probably the proximity of the earthquake. Another possible factor is the resonance or the synchronization or when the building synchronizes with the earthquake waves. Okay. So they can can simply shake like indefinitely until they fail. Okay. Okay. And structural damage is the leading cause of death and economic loss in earthquakes. Okay. That's why we have, or actually almost all building codes all over the world incorporate earthquake design. I think even the Philippines were quite strict in terms of earthquake building codes. What we have here is the 1970 Ancash earthquake in Peru. This is also known as the Great Peruvian Earthquake, okay, which happened in May 31, 1970, magnitude of 7.9, so it's quite big. And this is also known for a huge landslide in Peru, okay, and lots of casualties, around 60 to 70,000, okay, and 100,000 injured. Okay. And what you can see here is an adobe. Okay, you have here an adobe structure. Okay, mostly made of probably igneous or tuff. Okay, which is you can see here it's one of its walls were hollowed out. Okay. However, you can see on the background you have a concrete structure. This is a reinforced concrete structure which apparently suffered little damage. Okay, and we go back again to the Michoacan or the Mexico City 1985 earthquake. So it has two names. The Michoacan is the area of the source, and Mexico City was the most badly hit region during the earthquake. Okay. 1985, September 1985, magnitude of 8.0. It's large. Deaths of 5,000. And apparently the sort of the earthquake was offshore in the Middle America Trench, more than 350 kilometers away. So that's almost the distance between Metro Manila to Visayas. Okay. So despite the earthquake being quite distant at 350 kilometers away, Mexico City was still quite badly damaged, and one of the um, factors was the soil, okay, in Mexico City. So Mexico City is essentially sitting on an ancient lake bed, or the Tecnotitlan of the Aztec civilization. So the lake bed, okay, it was a double factor. Okay, you have a basin shape. Okay, so this is your lake bed deposits. Okay. Usually, when you have a basin shaped soil, and this is your incoming earthquake, okay, the tendency of the earthquake waves is to simply bounce around, okay, and focus the earthquake waves towards the center. And secondly, the fact that your soil is consisting of lake sediments. Okay? Lake sediments are quite known for being rather soft and unconsolidated sediments, okay? Mostly clays and silts, and their low stiffness can actually amplify earthquake waves. Okay, okay, especially the rather large earthquake waves. Okay? And add to that the resonance between the seismic waves and the medium rise structures. okay, are the buildings between 3 to 6 stories, which were mostly residential structures. Okay. And the damage was between 3 to 5 billion USD. Okay. You have like 412 buildings collapsed, 3,000 seriously damaged, and of course that it resulted in a significant change in the building codes in Mexico. This one is from the 1971 San Fernando earthquake in USA. So you can see here, this is like a shed for ambulances. Okay. And the shed apparently overturned, okay, pinning down the ambulances and rendering them useless. The other photo here is, I think, the same hospital. You have here a concrete column, reinforced concrete column. These are your reinforcements. Okay. And apparently, the vertical reinforcements were apparently sufficient. However, the transverse reinforcements or the reinforcements wrapping around the vertical rebars were not sufficient, okay, which resulted in buckling or like bowing of the column. Okay. Okay. The other hazard, and our next hazard is liquefaction. The key process in liquefaction is you start with a saturated soil, usually soil in along rivers or near lakes or near coasts, okay, with relatively open structure, okay, or relatively large pore spaces, which is common in unconsolidated or recently deposited soils. Okay. Now, once you apply seismic load or once the earthquake hits your soil grains will eventually be forced to rearrange themselves. Okay? And the arrangement of the soils into a tighter packing or a more consolidated state will eventually force out your water, okay, into the surface, and this can cause settlement, okay, in the ground. Okay. Also, during the rearrangement of the soil grains, you also reach a state wherein the soil grains are not in contact with each other. So you can see here, if we're gonna zoom in into the yeah. Okay. If you're gonna compare it to the first figure, you can see here that the grains are are in contact with each other and supporting the loads. Okay. So we call this in soil mechanics your soil skeleton being rigid. Okay. And the second diagram you have here your soil skeleton being disrupted to the point that the soil grains are not in contact with each other. And effectively the load is now being carried by your pore water. Okay. And at this point, water of course cannot carry load. And the result is that your structures or any load that's on top of your soil will eventually sink down. Okay. Now, we actually have two types of liquefaction. The most classic or the most commonly known liquefaction is the level ground liquefaction. So as per the term level ground, this one occurs on relatively flat or relatively level terrain. Okay. And this is caused by cyclic loading or cyclic liquefaction, wherein the liquefaction is simply, or the failure is simply driven by seismic loads. Okay. The cyclic loading, or of course, when you have earthquakes, the ground is shaking, okay, back and forth. So it's a cycle. Okay. Normally, liquefaction tends um, to be more, to worsen, or tends to be aggravated when you apply more load cycles into the soil. Okay. And this is common in big earthquakes. Big earthquakes usually tend to have longer duration and effectively more cycles of loading compared to smaller earthquakes. Anyway, the back and forth shaking and loading of the soils, okay, eventually generates large pore pressures, and this in turn results in zero effective stress, okay, because it will reach a point where the load is now being carried by the water, and this will result in almost zero shear strength. Okay, essentially a liquid which cannot carry loads. Okay, therefore your structures will sink. Okay. Cyclic liquefaction also causes lateral spreading, so essentially similar process, but in lateral spreading, you usually only get this in areas where you have a free space. Okay, sorry. This lateral spreading usually only happens in near river banks, okay, or near the coast where you have an open space. Okay, so this is your open space. Okay, so when this soil undergoes liquefaction, okay, when this soil undergoes liquefaction, okay, it is easily accommodated by this open space, and the result is that this mass can laterally move towards the coast or towards the river. Okay. And the usual feature of lateral spreading is you get very big tension cracks. Okay. Very large tension cracks behind the moving mass. Flow liquefaction is more of a 50-50. Not 50, but in this case, you have you have existing conditions which are not really that stable, even if you just consider the static loads. So what are the common examples here? Dams. Okay, dams which are not really well designed. Okay, can have more or less a metastable configuration. Okay, they're stable, but at the same time, they are the dam structure itself might be subject to large loads. Okay, and you essentially just need a little encouragement from the earthquake for the failure to occur. Okay, so this can liquefaction can also occur in high-rise buildings in liquefiable soils. So high-rise buildings, um, they exert they can exert a lot of or they can be quite susceptible to bearing failure. Okay, or meaning the soil can just easily rotate or turn with a little encouragement from earthquakes. Okay. Okay, so in this case, in flow liquefaction, you have a more or less slightly unstable configuration of your structures. in static loading or in a non-earthquake scenario. Now, once you introduce your earthquake, or once you introduce liquefaction of the underlying soils, okay, you only need like a partial loss of shear strength. You don't even need a complete loss of shear strength here. So you only need a partial loss of shear strength to trigger a failure. So in the case of dams, it would be a dam or an embankment failure. In the case of this high-rise structure, the failure is essentially a bearing capacity failure, okay, which was partly triggered by liquefaction. Okay, so in cyclic liquefaction, so again, in cyclic liquefaction, we have like near zero shear strength or very large loss of effective stresses. Okay? And the classic ground manifestations of cyclic liquefaction are sand boils, which indicate presence of very high water pore pressures. Okay? So essentially, these are like volcanoes. Instead of erupting lava, they simply erupt water. Okay? And when you have sand boils and you have it, it simply means you have very high pore water pressures, which also means that you are ejecting a lot of water out of the ground. And that would mean that there would be a large loss of volume in the ground, which can result in large settlement or large vertical settlement of the ground. Okay. So we have an example here from Christchurch in New Zealand. This one. So I was actually in New Zealand in the aftermath of the Christchurch earthquakes. So Christchurch earthquakes or a series of earthquakes, notably the 7.1 earthquake in September 4, 2010, and another one, a magnitude 6.3 in February 22, 2011. So in between these dates, there were also a lot of earthquakes in between. And the most impacted region was the city of Christchurch in New Zealand. Okay, so Christchurch is like the second largest or third largest city in New Zealand. Okay. Um, so I was there I was studying my master's in New Zealand back in 2014. And I saw the reconstruction of the city. Okay. And the biggest challenge to the reconstruction was money. Okay. To be specific, the biggest challenge was litigation. Okay. So why was litigation an issue in Christchurch? So apparently, some of the buildings during the Christchurch earthquake were like a certain percentage of the buildings were sustained minor damage. Okay, they had cracks, but structurally they were still structurally sound, meaning they can still be used. However, the owners, of course, were more concerned about would be concerned about replacing their whole building. Okay. And this, of course, was conflicted with the insurance agencies. Okay, so leading to there were a lot of bankruptcies among the insurance agencies as a result of the Christchurch earthquakes. And as a result, their reconstruction took like a lot of time. Okay, even if you compare to the Philippine standards. Even like 10 years later, they were not really even totally done with their rehabilitation efforts. Okay. So as a result, the original city center of Christchurch was not fully restored. So the city essentially just decentralized into smaller business areas. Okay. So it simply scattered around. Okay. Anyway, so what we're seeing here are liquefied neighborhoods in Christchurch. So you can see here, these are probably sand boils. Okay. And the gray stuff you can see are essentially liquefied soils, okay, mostly silts. So I'm just gonna show you one of the liquefied areas in Christchurch, the Shirley Intermediate School. Okay, so we're just gonna look at it in Google Earth. So you can actually see the changes in the satellite imagery between September 2010 and February 2011. So I'm just gonna enter the coordinates. Mm, okay. So this okay, so this Christchurch, okay. It's essentially a floodplain, okay. And this is Shirley Intermediate, okay. So let's travel back to September 2010. Okay, so this was before the earthquakes, right? So this is the date before the earthquakes, before the liquefaction. Okay, still before the liquefaction. Okay. Mm, okay, and this is after, okay, the liquefaction. So you can see here, you can see some something that looks like pock marks. Okay. You can see here a lot of pock marks around the building. So I think these are just sand boils. Okay. Okay. Probably sand boils. Okay. Okay. So I don't have much to discuss about Shirley Intermediate. Okay, let's go back to flow liquefaction. So again, flow liquefaction is about combination of static loads plus liquefied liquefied soil. Okay. So in contrast with cyclic liquefaction, where you simply have purely just liquefied soil that's driving the failure. Okay. In flow failures or flow liquefaction, okay, again, the common examples here are dam failures. Okay? Especially the 1971 San Fernando Dam. Okay? And other, you also have tailings dam failures. Okay? I think currently now, probably flow liquefaction in water or impounding dams might not be as much as a concern right now because the technology in constructing earth dams have drastically changed since the 1970s. Okay. Starting mid to late 1970s, they started implementing the use of clay cores, clay, or essentially the center for them will have a clay rich center, and clays are actually self-healing, meaning they can sustain displacement, they can sustain damage, because they can easily heal itself, okay, even if you deform the dam. Okay. However, for the case of tailings dams, I'm not sure about the technology for the tailings dams. Okay. Tailings dams usually are not really designed for long term operation, probably not as long term as for water supply dams. Okay. And this one is the Sheffield Dam, okay, which failed following the 1925 Santa Barbara earthquake in US. Okay. Okay, so the photo shows this dam underwent complete failure. Okay. And it was investigated by Seed and Idris in 1968. Okay, so that's like 40 years later. Okay, but this is a interesting read considering the technology at that time. So they were able to deduce what happened to the Sheffield Dam. Okay, just a background. The okay, this was the ground shaking during, or this was the uh, acceler accelerogram during the Santa Barbara earthquake of 1925. Okay, this is your time and this is your acceleration. So this is essentially written by your seismograph or your old school seismograph. So the classic one you see in the movies where you have a roll of paper and a pencil, which is sketching into the roll of paper as the earthquake is occurring. Okay, so I'm just gonna introduce to you the how to read an accelerogram. Okay, so you can see here some spikes, right? You can see some spikes in your movement, and usually the movement can go in a positive or negative direction, and it doesn't matter really what is the polarity of the movement. So this biggest spike we can see here is what you call the peak peak ground acceleration. Okay? So essentially it's the biggest acceleration of the ground during the earthquake. Okay? Most structures are sensitive. Most stiff or small structures are quite sensitive to peak ground acceleration. Okay. Slopes also can be quite sensitive to peak ground acceleration. And in here, the peak ground acceleration or the PGA is actually point 0.1, point 0.2 it is actually 0.15 G. Okay? G or units of gravity, your 9.81 meters per second squared. Okay? So PGA is usually expressed in G or acceleration due to gravity. So at least in this one, the dam experienced an acceleration that's about 15% of your gravitational acceleration. Right? So first question, is that a big PGA? Is that a big acceleration? At least in my work, I usually for just to compare, right? The big one or the potential earthquake from the valley fault system can produce a PGA of around zero point 0.4 to zero point 0.6 for the area around Metro Manila. Okay, so in this case, 0.15 might be on the low to moderate side of PGA. Okay, and this is the slope stability or this is the embankment stability analysis. So this is just the same as slope stability analysis, except that you're dealing with an embankment or a dam. And their smallest factor of safety back then was 1.21. Okay, meaning, sorry. So this was the pseudostatic, right? So this was done. Um, yeah, this is the analysis of the dam during the earthquake. Okay. So just accounting for the ground motion due to the earthquake, the factor of safety of the dam was 1.21. Okay. If we're gonna interpret that literally, it means that the dam would be stable, okay, if we only consider the ground motion. Okay. So meaning the acceleration due to earthquake was not really enough or was not the main culprit for the failure of the Sheffield Dam. And after that, what Seed and Iris did was they tried to factor in the effect of strength loss due to liquefaction. Okay. And yeah, essentially, this is what they saw. They saw that the dam would essentially slide laterally with a factor of safety of 0.75 if this zone underwent liquefaction. And this was corroborated, or this was consistent with what they observed in the field. Okay? Or essentially, you can see here the dam simply flattened out. Okay? Okay? So in modern times, when we calculate for stability of dams or stability of embankments, like for example, flood control projects with which use embankment fills or maybe tailings dams, you have to consider the loss of strength of the embankment materials due to liquefaction. So what usually happens is you first analyze the stability of the embankment purely due to acceleration, and then after that you will analyze which soil layers will undergo liquefaction during earthquake. And then the third step is to modify the proper, or in the stability model, you have to modify or change the strength properties of the liquefied soils or liquefied materials. And then you have to run another round of stability analysis. Okay. Okay. This one is another example of flow liquefaction. Okay. So flow liquefaction can also occur in relatively flat surfaces. Okay. So in this case, The Kawagishicho apartment buildings apparently were not really that stable even in static loading, okay? Because of course there's these are like medium rise structures constructed in relatively unconsolidated soils around the river banks, okay, of Shinano. Okay. So even without earthquake, these buildings are really quite susceptible to bearing capacity failure or essentially overturning. Okay, they can just fall down like a domino even without earthquake. Okay, and of course, with little encouragement from the 1964 Niigata earthquake. Okay, the underlying soils consisting of riverbank deposits underwent maybe partial liquefaction, and it eventually catalyzed or helped trigger the bearing capacity failures here. Okay, so okay, we are saying catalyzed because if this was purely just liquefaction, okay, what should have happened was that the building should have simply sunk down or settled down, okay, without overturning. Okay. So in a pure liquefaction or in a pure cyclic liquefaction event, what would happen is that the buildings will simply sink down. Okay. However, in this case of Kawagishi Cho apartment buildings, you can see here that the structures essentially um, underwent rotation at their base, or essentially they underwent bearing capacity failures. Okay, right? And this one is the San Fernando Dam. Okay, Lower San Fernando Dam. Okay, unlike in the Sheffield Dam, the San Fernando Dam only had a partial failure. Okay, so this is your reservoir, and this is your downstream. So at least, and you can see here that the dam was still quite intact and on its downstream portion. The only failure that happened was along its crest. Okay. So just for a context, the Lower San Fernando Dam, the construction was done using a hydraulic fill material. Okay. If you're not quite familiar with the hydraulic fill, it's simply a fill which was applied by mixing water with soil and then funneling. They simply funneled the slurry, okay, and just waited for that slurry to consolidate on its own. Okay. So is it a good construction method? No. Simply because it's not really properly consolidated material. I'm sure you have encountered the process of properly compacting materials in your under construction or engineering subjects. So normally soils will have to be subject to compaction by rollers or by tamping, and it has to be done by layers, okay, to ensure proper compaction. Okay, so that kind of compaction uh, is like the standard for modern embankment dams. Okay, so in the case of San Fernando Dam, what they used in their method was hydraulic fill construction, okay, which is essentially just mimicking. So this is not too different from the consistency of a fresh river deposit. Okay? It's unconsolidated, it has big pore sizes. Okay? So it was really susceptible to liquefaction. Okay? And they were quite lucky that the dam did not completely fail. Otherwise, they would have had 80,000 casualties. Okay. And finally, we have here a tailings dam failure. Okay, so this is a, I think this one is um, a more relevant concern if we're gonna be talking about seismic hazards. 'Cause, again, tailings dams are not constructed the same way as hydroelectric or water supply dams. Okay, so you have here the Tapo Canyon Tailings Dam, which failed during the 1994 Northridge earthquake. Okay, okay, so I think the failure was around here. Okay, and liquefaction caused the tailings dam to lose strength, and it had a 60-meter wide breach. Okay, which caused the tailings to flow downstream. Okay, so it also damaged their water treatment facility. Okay. Although fortunately there were no injuries or deaths at this for this case. Now let's talk about lateral spreading. Again, lateral spreading is caused by cyclic loading or cyclic liquefaction. Okay. So the failure is almost purely driven by liquefaction. So again, letter spreading is a bit more dependent, like as in the same way as in level ground liquefaction. The more cycles you apply, the worse or the more liquefaction that's gonna happen. Okay, and again, the number of cycles during earthquakes are correlated to the magnitude of the earthquake. Okay. And in turn, magnitude of earthquakes are correlated to the size of the fault that's producing the earthquake. Okay. Okay. Lateral spreading is common around water bodies, specifically rivers, river banks, and coastal coasts. Okay. And in particular, lateral spreading can be quite serious in port facilities, which are very, very expensive to repair, very, very expensive to disrupt. Okay. Okay. The richest man right now in the Philippines, his main business is ports. Okay. We have here the Showa Bridge in Niigata, Japan. Okay. So this was the example used by Kramer in 2000 for his textbook. However, when I checked some publications, apparently the failure of the Showa Bridge is still up to debate. Okay. In the perspective of Kramer, he thinks that the bridge collapse was caused by lateral spreading, okay, of the soils underneath. However, Yoshida et al. Are actually contesting that interpretation, and they think that the main cause of the failure of the bridge was actually the resonance of the bridge with the earthquake waves. Okay. Okay, so this is a contested example, but I don't have a lot of examples to use, so I just showed it here. This one is lateral spreading in Christchurch. Okay, it's along a bridge. You can see here there's actually a river in the background. Okay, so lateral spreading bridge. You also have here the 2010 Haiti earthquake. So as you know, Haiti is probably one of the worst in terms of economy and political stability and social strife. It's probably one of the worst countries right now. Like, okay, Anyway, the 2010 Haiti earthquake, was probably one of the contributors to the current state of Haiti right now. Anyway, Haiti earthquake was a magnitude 7 earthquake in January 12, 2010. Okay? And it essentially damaged their port area, okay? Which of course hampered the relief efforts, okay, after the earthquake. Right, let's talk about landslides as seismic hazards. Okay. I think one of the prominent feature of landslides when they are being triggered by earthquakes is that earthquakes trigger a lot of landslides, and but the most prominent landslides, of course, are the big ones. Okay, so earthquakes can trigger both big, medium size, and large landslides. But the most prominent landslides during earthquakes are, of course, the big ones. Okay, earthquake triggered landslides have destroyed buildings, disrupted bridges, or even blocked rivers. Okay, some of the landslides partially result from liquefaction phenomenon, but of course, it's really hard to study landslides because these are sloping areas. Okay, access to landslides are not really that easy. And even the characterization of the groundwater of the landslide source areas prior to their failure is also quite challenging to do. Anyway, this is the photo. This is a before and after photo of the landslide in Peru. So this is still part of the Great Peruvian Earthquake of 1970. You can still see here the palm trees, before and after. And in the after, you can see here there were no no houses left after the in the aftermath of the landslide. Okay. It was a 50 cubic million cubic meter landslide, okay, which covered an area of 8,000 square kilometers. So that is like an area probably the size of a province, okay, or size of a big municipality, okay, or probably close to the size of probably bigger than Metro Manila. About 25,000 people were killed. Okay. And yeah, so it's a really big landslide. Okay. Really catastrophic. Okay. We also have here the another landslide triggered by earthquake. As for context, this was triggered by the 1964 Alaska earthquake, also known as the Great Alaska Earthquake and the Good Friday earthquake, because it occurred on a Good Friday in March 27, 1964. 139 casualties. The earthquake lasted for 4 minutes, so that's quite long. Normally, earthquakes we experience here commonly maybe under less than 30 seconds. Okay, so 4 minutes is quite long. It's a magnitude 9.2 to 9.3 megathrust earthquake and the most powerful earthquake ever recorded in North America. And it involved a fault rupture of 970 kilometers. So that's almost as long as the whole Philippine fault zone. Okay, and the result, one of the results is this landslide along the government hill. Okay, and the school here was damaged by the landslide scarp. So I think this is the landslide scarp. Okay, and the building was like cut in half by the scarp, by the main scarp. We also have here another example from Taiwan, the Shiyufen Ershan landslide. And what's interesting here is that it's, according to studies, it's actually a bedding controlled landslide. Okay. And the bedding actually had a fault propagating along the bedding. Okay. So this is a sandstone and shale formation. And okay, so you can see here, I think this is the scarp or the detachment point. Maybe this is the failed portion. Okay. So this had a volume of 36 million cubic meters. It's quite big. Fortunately, the fatalities are not as large as in the Peru. It only had 36 fatalities. And it was apparently triggered by the 7.6 Chi earthquake in 1999. Now let's talk about retaining structure failures. Okay. So retaining structure failures are not really common, okay, during earthquakes, except for port area retaining structures. So as you may know, most ports usually are made from reclaimed area. Okay, so if this is your original coast, okay, and this is your sea, sorry, not straight line. Okay, so this is your sea. When you're constructing reclamation, okay, so naturally you will be dumping or putting in some fills. Okay. Okay. Sorry, I'm not really sure on how the construction is done, but at least I know that reclamations will always have a retaining wall, okay, or retaining structure. Okay. The purpose of the retaining structure, of course, is to support the fill, okay, so that it doesn't, to provide confinement to the reclamation fill. Okay. Okay, so this fill is subject to horizontal movement, and the purpose of the retaining wall or the retaining structure is to prevent that lateral movement. Okay. Okay, so if there is a problem with the retaining wall or the retaining structure, the fill will undergo extension and there might be some cracks or any extensional features, okay, around the contact between the fill and the original ground. Okay. So one of the most prominent examples of retaining structure failures, particularly on a reclamation, was the port of Kobe, Japan. Okay. They had extensive damage to quay walls. Okay. Okay. So it was so serious to the point that their port was originally the sixth largest container port in the world. Okay. After the 1995 Hyogoken Nanbu earthquake, the port was completely closed. And then after 2 years, they tried to revive the port and they had to spend like 10 billion US dollars worth of repairs. But even after the repairs, the port only ranked 17th in the world. Okay, so it never recovered its status. Okay. Okay, and this is a photo from the Roko Island in Kobe, the port which I was describing. Okay, so you can see here, I think you can see you can see here at least there's already some scarp, okay, or some sense of detachment. Okay. And you can see here that the wall itself is not really aligned anymore. So this one probably underwent more lateral movement than its surroundings. Okay. Although its surroundings also underwent lateral movement. Okay. Okay. So this was caused by the Great Hanshin earthquake of 1995. It had a magnitude of 6.9. Tremor lasted for 20 seconds. It caused 5,000 casualties, okay, most of them from Kobe. And it was the second deadliest earthquake in Japan, okay, just after the Greek Kanto earthquake, which had like 100,000 casualties. Right? I think we're almost done. We also have now the lifeline hazards. I think this is more of a special kind of seismic hazards owing to the extensive reach of seismic hazards. Okay, during earthquakes, large areas can be affected by earthquakes and fault rupture. Um, when we talk about lifelines, lifeline networks can include your electrical power, telcos, transport, water, sewage, oil and gas, waste systems, and they're all called lifelines. So they all lend to the quality of the life of the bed of developed areas. Okay. So similarly, lifeline systems can include your power plants, transmission towers, harbors, airports, okay, solid waste landfills and stuff. Okay. And we have here a few examples. The first one is the San Francisco fires in 1906. Okay. What's bizarre in this case is that after the earthquake, they had fires in San Francisco, and unfortunately, due to the bursting or due to the damage of the water utilities, they were unable to fight or they were unable to put out the fire. Okay, simply because they had a problem with their water supply. Okay, also due to the earthquake. Okay, so it was like the second photo is from the 1989 Loma Prieta earthquake, okay, again in San Francisco, and a lot of water mains or water lines were damaged during the earthquake. And here you have a photo of damage to an electrical substation and collapse of a transmission tower in Turkey, in Hatay, Turkey, in February 6, 2023. So this earthquake is quite interesting because Turkey, I mean, to be honest, Turkey is supposedly one of the leading countries when it comes to earthquake engineering. Yeah, I'm not kidding here. Turkey is, if you're gonna you're gonna look up some research about earthquake prediction or earthquake forecasting. Turkey is probably one of the leading countries to do research on predicting earthquakes. Um, Even within Europe, they host probably one of the top universities involved in earthquake engineering. I think one of them is not sure if it's the University of Istanbul, not sure. But anyway, Turkey supposedly had one of the most comprehensive earthquake building codes in Europe because their building code supposedly is like an amalgamation or a combination of Japanese, Californian, and US. Sorry, California is US. Japanese, US, and other building codes around the world. Okay. However, supposedly due to corruption, the building codes were not really followed. Okay. And the result is they had a lot of damage to their structures. Okay, especially the new ones. Okay. I think you probably saw this in the news back in 2023. There were photos of old buildings in Turkey which did not collapse. Okay. Old buildings made using the old regulations. While you have new structures collapsing, okay, because they had new regulations, they had stricter regulations, but they're not really followed properly. Okay. Okay, and finally we had tsunami and siege hazards. Okay, tsunami. When you're talking about tsunami, the essential recipe for tsunami is large vertical displacement. Okay, okay, offshore. Okay, and tsunamis are commonly generated by, of course, faults with large faults with large vertical components, namely your especially the thrust faults and trenches. Okay. So tsunamis are quite treacherous because they have when while traveling in the open sea, their wave heights are usually less than 1 meter, while their wavelengths would be several hundred kilometers. So while they're traveling at the sea, they will have a really, really, really short or a small profile, but a really long wavelength. Okay. Now, once they approach the shore, the wave sort of compresses laterally. So it's like a car that's hitting a wall. So this wave, which is originally like small wave height, long profile, as it approaches the shoreline, this wave would eventually bunch up. Okay, it would eventually bunch up into a short wavelength but large amplitude wave. Okay, which can of course be quite damaging and can reach for a quite distance inland. Okay. So the Great Hoei Tokaido non-hydro tsunami killed around 30,000 people in Japan in 1707. The 1960 Chilean earthquake produced a tsunami which killed people in Chile, in Hawaii, and in Japan. And you also have the 2004 Sumatra earthquake, which caused a tsunami which killed more than 200,000 people in Indonesia, Thailand, India, and Sri Lanka and Myanmar. And also triggered the development of tsunami warning systems in the world. Okay, so the US, no, I think has an extensive sorry, not only US but also Japan. Japan and US have an extensive tsunami warning systems around the world. So it's normally consisting of buoys or like floating balls, which can sense the depth, okay, their current elevation, so they can sense the movement of your tsunami wave. Okay, so they are spread across the ocean, and collectively they can detect or measure the movement of tsunami wave. Sorry, tsunami lang pala. Okay, so this is the aftermath of the Sumatra earthquake in Indonesia. Okay, it took it was triggered by the magnitude 9.2 to 9.3 earthquake with an epicenter from the west coast of Aceh in northern Sumatra, Indonesia. It occurred in December 26, 2004, and the earthquake was an undersea megathrust earthquake. Okay. Caused by a fault between Burma and the Indian plate. And the tsunami wave heights were as high as 30 meters, so that's like a 10-story building. Um, Killed an estimated 227,898 people in 14 countries. And it was the deadliest tsunami in history, the deadliest natural disaster in 21st century, and the deadliest natural disasters in recorded history. Most powerful earthquake ever recorded in Asia. Most powerful earthquake in the 21st century. And the longest fault rupture ever observed, with a fault rupture length of 1,200 to 1,300 kilometers. So that's about as long as the whole Philippines. Longest duration of shaking, at least 10 minutes. So that's freaking long. And it also caused the entire planet to vibrate as much as 10 millimeters, and also triggered earthquakes as far as Alaska. And we have another example here, tsunami in Japan in the 2011 Tohoku earthquake. I think this is more famous for the Fukushima Daiichi nuclear meltdown. Okay. The story here is that the tsunami the nuclear power plants actually had a protective sea wall or a tsunami wall. So they actually designed the wall to withstand a tsunami. And the approaching tsunami actually, once it hit the wall was actually stable, right? So when the tsunami wave directly hit the wall, okay, the wall was able to resist the direct hit. However, the tsunami eventually breached the wall, and its return as the tsunami wave returned to the ocean, it actually dragged the wall over. Okay, and of course, subsequent waves eventually damaged the nuclear power plant and caused a meltdown, or meaning the nuclear waste eventually leaked out and discharged into the ocean. Okay, and overall, this tsunami resulted in damages of over 300 billion US dollars, probably the costliest natural disaster in history. Okay. The earthquake itself was caused by a magnitude 9 to 9.1 undersea megathrust, okay, in the east of Oshika Peninsula. The earthquake lasted for 6 minutes, and it's also known as the Great East Japan Earthquake, and it's currently the most powerful earthquake ever recorded in Japan. And the tsunami, okay, had waves which were as high as 40.3 meters and had a velocity of 700 kilometers per hour. Okay. And the tsunami reached inland as far as 10 kilometers. Okay. Seisures are in a way similar to tsunamis, but they usually occur in enclosed bodies of water like lakes or large rivers. Okay. And these are usually caused by long period oscillation. So if you want to visualize a seiche, you can just get a glass of water, okay, and just try to agitate the glass slowly. Okay, so eventually, as you slowly move your glass of water back and forth, the waves can eventually can undergo constructive interference and form really large waves. Okay. Okay. We had seiches in the 1964 Good Friday earthquake in Alaska, having waves as high as 5 feet. And seiches can also occur in dams, in the reservoir of the dams. Okay. And that concludes the lecture on seismic hazards. So far, do you have clarifications or questions?
None so far po.
Okay. Okay. If there are no questions, that concludes our session for today. Thank you for attending and have a good evening.
Thank you po.